Hi everyone, we're now going to apply the power-reducing identities, the PRIs, which you use all the time in calculus, especially Calculus 2, Math 151, because calculus hates squares. Calculus hates squares. It doesn't really like them for derivatives when you're differentiating, and it really doesn't like them for integration when you're integrating. So for example, let's express cosine squared of 2x. Maybe you have to integrate this in Calc 2. Express cosine squared of 2x in terms of first powers of cosines. What? Well, I might frame it like this. Rewrite this expression in such a way that you can fill in these boxes with real numbers. So express cosine squared of 2x as potentially a real number plus or minus a real number times cosine of a real number times x. Something like that. Expressing cosine squared of 2x in terms of the first powers of cosines. Notice that there's no exponent here on cosine. The implied exponent is 1. So that's what I'm talking about. Rewriting this something more like that. And in fact, we can express this in this form, where we choose the sign appropriately. Okay, so we could do a basic substitution. We could let u be 2x. You don't have to do that, but it could help. And what's the PRI for cosine squared of u? Well, it's 1 plus cosine of twice u, that 2 is very important, all over 2, where u is 2x. Now you might be thinking, well, hey, this fraction looks uglier. It's a fraction. I have to double the argument here. Maybe, but at least it doesn't have any squares. Again, calculus hates squares. Calculus would rather deal with this right-hand side than this left-hand side. This is very easy to differentiate and integrate. And remember, sin is bad, sin is negative. The plus sign goes with the cosine or cosine squared version. All right. So cosine squared of u, if you want to do a sub, cosine squared of u is 1 plus cosine of 2u all over 2. Here I basically sub back. And what is twice 2x? What's the argument up here? In a way, that's one of the prices you pay for using the PRI. Yes, you're getting a fraction, and also you're doubling the argument. Sometimes you make it worse. But at least there are no squares here. Well, you get 1 plus cosine of 4x all over 2. Twice 2x is 4x. And really, we're done here. It was a short problem. Really, we're done here. We're expressing this in terms of the first powers of cosines, and we've simplified. So basically, this is the correct answer. But if I frame the problem like this, where I ask you to fill in the boxes and choose the sign, then you would have to go, okay, so this is going to equal, if I break up the fraction, we have 1 over 2, we have 1/2. It turns out to be a plus sign here, so you choose the plus sign. And then we basically have 1/2 cosine of 4x. A cosine of 4x over 2, that means that the 1/2 can pop out. And we have cosine of 4x. I guess I put a box here too. I might give you the 4, but now cosine of, it's a 4x over here. All right. So this is 1/2 plus 1/2 cosine of 4x. 1/2 plus 1/2 cosine of 4x. Again, we're writing this in terms of first powers of cosines, and calculus really loves to take the derivative or the integral of this thing. It can do it term by term. Okay, next up, the 8 identities that you don't have to memorize, but if I give you the appropriate block, if I give you the block of product of sum identities here, these 4, or this block of sum to product identities, these 4, then you can pick which one to use and apply it appropriately. It sounds simple, but many students actually don't get full credit on exams. They make some mistakes. First off, let's apply a product to sum identity. I want to express this product, sine of 6th theta times sine of 4th theta, as a sum. For a similar reason as for this previous problem, because calculus does not like products or quotients so much. Calculus would rather work with sums or differences because it's easier to take derivatives or integrals term by term. So calculus likes to break products up into sums or differences. Now, I'm being nice. If I give you a problem like this, then I will let you use this block of 4 identities. It might be helpful to put parentheses. Okay, pick which one to apply and apply the appropriate identity. So over here, we have sine of u times sine of v. You could even switch these. Right? Well, it turns out we want to use this first template, this first identity, sine of u, sine of v. It doesn't even matter who's who. All right, so this is the identity we apply. 1/2 times all of this, cosine of u minus v, minus cosine of u plus v. By the way, it doesn't even matter who's u and who's v, because over here, of course, u plus v equals v plus u. So this guy here doesn't care which is which. But even this over here, if you put in, whether you put in 6 theta minus 4 theta or 4 theta minus 6 theta, well, they're opposites of each other. And cosine is what kind of function? It's even. So it doesn't matter if you put u minus v or its opposite, or you switch these guys. It doesn't matter. Either way, it'll work out. So it doesn't matter which guy's u, which guy's v. All right, anyway, let's apply this directly. Sine of u times sine of v. We pick this first identity here, equals 1/2 times the cosine of u minus v. That's 6 theta minus 4 theta. All that minus, well, the 1/2's in front of all this, but all of this minus cosine of u plus v. U is 6 theta, v is 4 theta, or you could have switched them. Right? Then you simplify. Some students don't bother simplifying. I do want you to combine like terms in here and in here. 6 theta minus 4 theta is 2 theta, and 6 theta plus 4 theta is 10 theta. And it turns out this would be an appropriate final answer. 1/2 the quantity, cosine of 2 theta minus cosine of 10 theta. And again, calculus has a fairly easy time differentiating or integrating this. Now, what are some mistakes that students make? Well, like I said before, students may not bother simplifying. I do want you to simplify this and this. What's a common error? Students try to combine these, almost like they're like terms or something. They're not, okay? And also, the difference of cosines is not the cosine of the difference, okay? We don't have a factoring or distribution rule that works here, okay? A lot of students think that this is equal to cosine of, they think, oh, 2 theta minus 10 theta is negative 8 theta. No. No, 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 no. I've just written this, but no, 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 no. Okay, that doesn't work. We don't have a rule that says that. It doesn't get much better than this. Okay, there's no way of rewriting it in a way that's really better. If you want to distribute the 1/2, that's fine, but do not do this because this here is not equivalent to this inside here. That is outright wrong. So I'm going to erase all that. Another common error, surprisingly common, people don't bother to cross their thetas. So they write 20 here, basically, and they write 100 here, and they don't bother to cross your thetas. Folks, cross your thetas. That one stroke can end up giving you full credit. Don't just leave this as an O or a 0. That's wrong. Cross your thetas. I sound like eat your vegetables. Cross your thetas. It's not that hard. Boom, there you go. I'm not going to get a ruler, okay? Boom, there you go. Okay, so cross your thetas, and again, don't try to simplify inappropriately. This is not cosine of negative 8 theta. You're not allowed to do that. Just like over here, right? Cosine of u minus v, we had a full-blown identity for that. It wasn't just cosine of u minus cosine of v. So again, that was helpful for a calculus application, like integration. How about the sum to product identities? All right. Well, how about the sine of 6 theta plus the sine of 4 theta? In which case, Okay, you want to look at this block of sum to product identities. You don't have to memorize these. I would give these to you. But you have to know which one to apply and be able to apply it correctly. All right, sine of 6 theta plus sine of 4 theta. Again, we can do a snap substitution if you wish. Here I use x and y. I'll call 6 theta x and 4 theta y. And again, because of commutativity, it doesn't even matter in this case, just like last time, because look at the right-hand side over here. We're going to use this first identity, sine of x plus sine of y, sine of x plus sine of y. I'm going to use this first identity, all right? We'll look over here. If you switch x and y, well, x plus y is the same as y plus x. They're equivalent, right? And again, for cosine, even though x minus y and y minus x are opposites, cosine is even, so he doesn't care. So you could switch these. But here, let's call 6 theta x and 4 theta y. And for the templates with the minus sign, it does matter who's who. Probably. Again, right off the bat, when I say simplify this, students may be tempted to rewrite this as sine of 10 theta. Oh, I want to simplify this. I'll write this as sine of 10 theta. No. Okay, don't do that. You're not allowed to do that. It's almost like they're trying to combine like terms or factor or something. Do not do that. You cannot factor out sine. You're not allowed to factor out a function. You cannot factor out sine. Sine of 6 theta plus sine of 4 theta. If you think you can do this super easily and re-express this, you're doing it the wrong way. You need this kind of identity, this right-hand side, which is not that easy. All right. So using this first identity, right? Sine of 6 theta plus sine of 4 theta, sine of x plus sine of y equals 2 sine of, x is 6 theta, y is 4 theta. I'm putting these as reminders. That's over 2. That sum is over 2 times cosine of 6 theta minus 4 theta. That's x minus y, 6 theta minus 4 theta, all over 2. Okay, work out these arguments. You have to work these out to simplify. 6 theta plus 4 theta is 10 theta. 6 theta minus 4 theta is 2 theta. We can start there. And then inside these arguments again, half of 10 theta is what? It's 5 theta. 2 theta over 2 is just theta. So we get 2 sine of 5 theta, cosine of theta. And that's about as good as you can get this if you're going to apply the sum to product identity. Now, where might you want to do this? Let's say I ask you to solve. I won't in our class, but let's say I ask you to solve this thing equals 0. Now, we don't have so much a sub-method for solving equations, but we do have the zero factor property, a factoring approach to solving these kinds of equations. So that's why it might be good to re-express this here as a product. So then you would set this equal to 0. Okay, and you would then solve this thing here equals 0. So you set sine of 5 theta equal to 0, solve that. Set cosine of theta equal to 0, solve that, and you get the full solution set. That takes some time. And I would not give you that kind of a problem on homework or exams, but you could do that. In calculus, maybe you will have to someday. It'll take some time, though. Okay. And also, you can use the identities to build up triple angle identities, like sine of 3u and so forth, in principle. All right. Next up, in our final video for sections 5.4 and 5.5, where do we apply these identities in calculus in a big way? That's next time.